You blame it all on the clock, by the way, because this clock started to do weird, so we lost track of time. The last speaker is Simon Willerton from Sheffield, also known as one of the Catsters on YouTube. So he's going to talk about 2-2 traced.
Right, okay. So, firstly, as the last speaker, I thank the organisers for another interesting conference. So, if we just thank Okay, so what do I mean by two traces, first of all? So two traces are going to be sort of traces on two categories. So we've seen quite a lot of the idea of traces on monoidal one categories, and I want to give you some idea of how you can define traces on two categories. So, and there'll be two of them, hence the title. Right. So what I'm going to do is I'm going to give you lots of examples. So hopefully an example each of you can sort of deal with. So first of all, I'm going to be using string diagram notation, which we've seen for monoidal categories. So now we're going to use it for bi-categories. So or two. Don't worry about whether I say bi-category or two category. I'm not going to worry about the technicalities of the difference. So the point is what we've got is we've got some two categories. So we've got objects. This is the traditional notation, sort of little green dots. We've got morphisms between the objects, and we've got two morphisms between the one morphisms. Okay, so in string diagram notation, we take essentially the Poincare dual of this. So the objects now become sort of portions of the plane. So X now becomes this region here, Y becomes this region here, the arrow, red arrow here becomes the sort of the thing dual to it, so it's just something cutting through perpendicularly. So we just have this line, will just correspond to that one morphism, and this two cell now becomes just a point, a black dot. So that's how I would represent a two morphism in a two category, and then we can do slightly more interesting things. So if we compose them, so this sort of pasting diagram, we've got two cells which are all glued together in this way. So here we would have, we're just gluing them together, so we get a little two cell here which goes from the composite of two one morphisms. So if we just look at half of this diagram, we've got the composite of two morphisms, two one morphisms, so that's we put a dot and followed by another dot. So I always read my diagrams in the convention is that diagrams go from my side to that side and from the bottom to the top. So we read this as this is a two morphism from the thing at the bottom. I can put labels on this, so the composite of three one morphisms to the composite of two morphisms, and it's formed by these three two morphisms. And so we're actually going to want a monoidal structure, and so we're going to want to be able to tensor objects together. So given two objects, we want to form a third, which is the tensor of them, and do similar things for the one morphism and two morphisms. So to do that, I'm going to have to use a third dimension. So I'm going to represent tensor product. So here, this is supposed to represent a one morphism. So here, the purple region, this is supposed to be a plane coming out of the plane of the board here. So this is supposed to be read as a one morphism. The little red dot is one morphism from X tensor X primed. Okay. Backwards into the board is the tensor direction, so I read it. The front X tensor X primed, I'm going in that direction, and I'm going to Y. So this is a one morphism from X tensor X prime to Y. And here, if I want to have a So maybe give you an example of a two-morphism. So we've not just got this sort of planar picture here. We're allowed to have sort of sheets of paper which can join together. So again, we read this by we look at what's at the bottom and as our source. So this is a two-morphism which goes from I tends to j. If you look at the back, I tends to j, and then you can compose it with h. So that's the source at the bottom, and then it's a two-morphism to k. So I've just realised it's probably bad doing these unless I give you some nice examples of monoidal bicategories first. So let's just have a look at some examples. Okay. So I'm going to think about these sort of 6 examples. Hopefully, like I say, you will have some familiarity with at least one of them, or be able to get reasonably comfortable with each one of them. I'm not necessarily expecting you to be happy with all of them. So, simplest sort of monoidal bicategory I can think of is the bicategory of spans. So the objects here, so the objects are sets. And a morphism from x to y is another set with a map from with a map to x and to y. And given 2 of these, you compose these by taking this pullback. So if you've got one from w to x and you've got one from x to y, these are just sets with maps down. You can just take the pullback over x, and that'll give you a set up here with maps from maps down to w. Map down to y. And so these are your one morphisms, but we want to have morphisms between our one morphisms, and these will just be, if we have 2 spans, so z going from x down to x and down to y, and we've got another one going from down to x and down to y, then a 2 morphism is just a map from z prime to z, so that diagram can be used. So you can, I mean, if you've not seen this before, then you have the category of sets, and you can sort of, slightly vague here, but you can map this into the category of spans. So obviously, a set will just go to a set, and as a morphism, if you have a morphism from x to y, then you can draw it the other way around, from x to y, you can draw it so you just, on the right hand side, you just take the identity map, and on the left hand side, you just have the map F. And then you can check that the composition, if you have 2 maps, if you had another one, sort of W, if you had a map G from W to F, then the thing you get up here will just be W, and this map here will just be the composite. So this is just some sort of jazzed up version of sets, and we'll see why we want to jazz it up a bit later. So we've also got a monoidal structure. So we've got our one morphisms, 2 morphisms, and we've got a product. So we can just use the usual Cartesian product of sets. So we can, if we've got another 2 morphism, we can just consider it. We've got one of those, and we've got another one. We can just use the Cartesian product and form another 2 morphisms. So I've got the ordering wrong way around here. I'm getting tired, sorry. So we can just, given 2 of these, we can just multiply them together. So we get this monoidal structure. So similarly,
this is Dagger category.
No.
No.
We'll come to what structure it has a bit later, but it's not Dagger. Okay, so then we've got the category of bimodules. So here, let's just work over the complex numbers. So we can take as our objects, we take algebras, or monoids if you like, in the category of vector spaces. So the objects in this case are just going to be, the objects are algebras, the morphisms from one algebra A to another algebra B, we just take to be the bimodules, the right A, left B bimodules. And how do we compose two of these? Well, we just tensor over the algebra in the middle. So that gives us a nice structure on those. And so we need to have also our two morphisms, so morphisms between these things. So a morphism from an AB bimodule M to an AB bimodule M primed is just the sort of module map, so the things that commute with the action A and B. And again, we can tensor things together, we can tensor over C. So given two algebras, we want to get a third one, we can just tensor these two algebras over the complex numbers. So we can just use that structure. And this gives us a monoidal two-category structure. Okay, so something for the sort of the category theoretic hardcore amongst you. You can look at enriched profunctors, so this sort of generalises both of these two categories. So I won't say too much about it because if you know what it is, you don't need me to tell you. But we're just enriching over some monoidal category. The objects are the enriched categories. The morphisms are these profunctors, V profunctors. We have a tensor. We can compose very similarly to what we do in the bimodule case, and we just take the V natural transformations between these things as our two morphisms, and there's a tensor product of V categories. So we can tensor two V categories together and get a new V category. So this is sort of the many objects version of an algebra. So algebras are sort of one object vector categories. So slightly more, going to a more topological example. So we can take the two category of two tangles. So in this case, we have our objects are just points in the plane. So the plane here is being this purple plane. And so we'll just take a finite number of points in the plane as our objects. And so a morphism from one set of points in the plane to another set of points in the plane, we'll just take it to be tangles in R3. So that just means ways of joining up these points. So, and these are sitting in R3. So composition is just composition of tangles. We've got a tangle here, we can just glue on, and we've got a tangle from another set of points to these set of points in the middle, and we can just glue these two tangles together to get a new tangle. That's just the composition of one morphisms, and two morphisms between them are going to be cobordisms in R4. So maybe let me just switch to another picture for 1 second. So the idea is that some tangles with some cobordisms. So we've got the two morphism is going to be something going from one tangle to another tangle. So here we've got a pretty simple tangle at the top, just these cup and a cap, and just this cross at the bottom. And this surface, which goes from the tangle at the bottom to the tangle at the top, is supposed to live in R4. So here we've got these tangles living in R3, and then we've got this extra direction, and we've got an embedded surface inside R4, whose boundary is the tangle. And this is just showing you how you can compose these in the three different ways: the tensor product, the composition of one morphism, and the composition of two morphisms. So if we have two cobordisms, then we can use the tensor product, which for tangles is just a disjoint union. So we're just going to stick them together in this direction going into the board, so we can stick one in front of the other. That's our tensor product, but we've also got the composition from the composition of one cell. So remember, that was just glue two tangles together, so we glue them together in that direction. Or we've got the composition of two morphisms, so this is our sort of vertical composition. So we just stick one cobordism on top of another one where we've got this angle column in between them. So that's a more topological kind of monoidal two category. Now my interest really was in this, really came from the following example, which I don't know it's terribly appropriate for the audience. But the objects in this case are complex manifolds, or I guess non-singular projective varieties. The morphisms, the one morphisms are between x and y, are complexes of sheaves over the product. So this is somewhere between these two examples, except instead of algebras or sets, we've actually got complex varieties here. So this is like, as we've sort of seen, this is supposed to be like some sort of sheaf over the product x across y. And you can compose them by, there's a sort of convolution if you've got another sheaf over w cross x. There's something which is a bit analogous to this pullback operation. You can compose two of these together. And we've got the sort of two morphisms. You just fundamentally take, if you've got another complex of sheaves, you'll just take the sheaf maps running between them. But we want to do it slightly more jazzed up, so we take the x group. So the morphism category from x to y is going to be the derived category of sheaves on that. And we can just use the usual, again, the usual Cartesian product of manifolds. We've got a manifold W and a manifold X, then we can just take the product W cross X as our sort of monoidal structure on this bicategory. So we can compose in these three different ways. And then sort of the algebraic version of that, which is just, again, it's just a jazzed up version of this bimodule case, is we can just do the same thing here, but we use sort of differential graded algebras, complexes of modules, derived tensor product, and X groups. It's just got a lot more structure. There's a lot more homological algebra, a lot more interesting information in this. This is a nice one to play with, but this is where a lot of structure is going on. So it's these sorts of ones that I'm really interested in, but these are also nice ones to look at. So things like Kavanagh homology, if anyone's heard of Kavanagh homology, is supposed to be some sort of monoidal two-functor from this category of two tangles into possibly one of these. So you're starting off with things like tangles, and you're ending up with complexes of modules or complexes of sheaves. So that was sort of one of my motivations, was trying to understand what kind of structures were going on in there. So these are the examples I've got in mind, and I'll keep on returning to these. So hopefully, so at least one of them on there which takes your fancy. Okay. So let's go back and ask, sort of, what is a trace? So, yes, to a mathematician, a trace means some function on something which satisfies something like this. I mean, so if you're teaching linear algebra, then you look at vector spaces and you look at endomorphisms of vector spaces, and you can define the trace of an endomorphism. Now, it's something that's always bugged me. I mean, what is the trace of an endomorphism of a vector space? I mean, if I've got an endomorphism and I take the determinant, I know what that is. I mean, the determinant is telling me I'm starting off with, maybe I've got some shape in a vector space, I apply an endomorphism, I end up with some new shape, and the determinant is telling me how the volume of that shape is altering. So I've got a good geometric intuition of what the determinant of an endomorphism is. What the geometric intuition behind a trace is, I mean, I really don't know. It's something I've been trying to think about for a long time, and I've got no real satisfactory answer. I mean, how do you do it? You pick a basis, you write down a matrix with respect to the basis, and you sum up the diagonal entries. It's not a terribly invariant thing to do. And then, if you're teaching this to students, you want to show that this is invariant under similarity of matrices, so that if you multiply, if you change bases, I mean, this is basically saying if you change bases, multiplying by change basis matrix, then you get the same answer. So it's invariant under change of basis. This is what this relation is telling you.
Sum out does the same relation there? Or isn't the bottom one just a consequence of the...
Very good, yes. Okay. So the bottom one is a consequence of the top one, certainly. I mean, this is sort of the one you see first, and the one that is important when you're doing character theory. If you're doing representation theory of groups and you want to define the characters, then this is sort of the relevant thing. as you well know, Brits, of course. This is often the thing you see when you're defining traces for algebras because things don't have inverses. So these things look like they're essentially the same, but what we're going to do is categorify this sort of idea, look at this at high categorical level. And although these are pretty similar down at the one category level, when you categorify things, you can categorify two things which are equivalent down at the one categorical level, but when you categorify them, they give rise to two different things. So that's the point I want to make here, is you have to be careful what you categorify. So in some situations, you wouldn't have inverses. If you've just got an algebra, you define a trace on an algebra which satisfies this. The elements in the algebra might not have inverses. So these are two ways of thinking. Okay. So what we've seen quite a lot of is one approach to traces in monoidal categories. So if we have a monoidal category, C tends to 1, then we have a left dual if we have these evaluation and co-evaluation. Now notice I'm drawing my my monoidal category again. It's supposed to be, these purple planes are supposed to be coming out of the plane of the board here. So my monoidal category, I'm not assuming anything like being braided or symmetric, so I have to be slightly more careful than some people have been so far this weekend. So we have a left dual if we have an evaluation map going from V star tends to V to the unit element, which I draw like this, and a co-evaluation map going the other way to V tends to V star, which satisfies the snake relation. So when I stick these together appropriately, we get an equality between this composition and the identity morphism from V star to itself. So, and similarly, we get an equality between this one morphism and that one morphism.
Sorry, V's are one morphisms or zero morphisms?
No, V is an object in the category.
Okay. So don't we want these, don't need to be true up to coherence? Oh, sorry, this is just a monoidal category.
This is just a monoidal category. Sorry, I'm doing the stuff that you know very well. Yes, obviously in a confusing way. But so this is just a definition of left dual in a monoidal category. And similarly, we have the notion of right dual where we switch them around. So V and V star are bidual if V is also left dual to V star. So for that, what I'm going to need is exactly the same thing. So I'm going to need another evaluation map and another co-evaluation map which satisfy analogous things but with V and V star. So I'm going to end up with two cups and two caps. I guess cups and caps are on the side here, so sort of spilling cups. So if that's the case, if we have a bidual for an object in our category V, and we have an endomorphism from V to itself, then we can define the trace. So the trace of the endomorphism, we just use this co-evaluation map. So we start at the unit object, we apply F to V, we do nothing to V star, and then we use the other evaluation map. So the evaluation map that isn't this one, the fact that we've got a bidual around us. So the trace of a morphism is just a morphism from the unit object to itself. Now in getting back to our sort of undergraduate example, if we take our monoidal category to be vector spaces with the usual tensor product, I say usual, this Bob actually defined it yesterday, with the complex numbers as the unit element, so that then the trace of an endomorphism is just a morphism from the complex numbers to itself, a linear map, so that just gives us a complex number, and that gives us the usual trace on finite dimensional vector spaces. Now, it's a sort of a slightly odd way to define a trace on vector spaces, because when I'm teaching undergraduates, I don't tell them about categories and monoidal structure. Well, I mean, you don't need to know that vector spaces have a monoidal structure in order to define the trace on vector spaces. So this is, although this is a very good and, well, incredibly useful notion of a trace, and it does capture the usual notion of trace on vector spaces, I always find it slightly odd, you know, that this is the way that we define the trace on vector spaces in a categorical fashion. It does, you seem to use a lot more technology than we usually give our undergraduates.
How do you prove that the trace is uniquely defined? Because obviously the cups and caps aren't uniquely defined.
The cups and caps aren't uniquely defined. Okay, so there's 2 points of view here. I guess I've said that V has a bidual, so I guess I'm implicitly using that bidual. Or you can show that if it has another bidual, where you have to be slightly careful when you do that. But when I'm saying it has a bidual, I'm saying, yeah, use the one that you give.
Am I right in thinking that this is a special feature of category of vector spaces? That it's possible in other monoidal categories with duals for the trace function to depend on which cup and cap you choose. Do you see what I mean?
Well, you need a pivotal structure.
Yeah.
But
Okay, and that you won't. Okay, whatever that is, you won't always have that. So you're just lucky that.
probably you always do. It's never known that you don't. Okay.
Right, so, but I haven't
No way.
shown you that this satisfies the trace property yet. I mean, remember that's what a trace was, something that satisfies these axioms and so forth. So, I've gone for the next. This is another area with horrible terminology. So I've gone for the one that Bob used yesterday, which was transposing. So if we have an endomorphism, I guess I've switched from, I was using V in my monoidal category here. So if I've got if I've got a morphism in my category, so again we're just in monoidal categories here, not two categories. I've got a morphism, then I have to say it's got a transpose, or another term, this terminology is it's cyclic, if, well, I've got a map from Y to X. Now, I'm assuming both of these have got biduals. So the usual thing is if you've got a map from Y to X, you can get a map from X dual to Y dual. We can switch them around and turn them into duals. And because we've got biduals, there's two ways we can do that. We can use, there's two pairings of the cups and caps we can use to switch them around. Now it's not necessarily going to be true, so this thing in the middle is just F, so we go X dual, here's an X and that's a Y. Turning the Y star, so that's just an ordinary F in the middle. But we could have come at it in these two different ways using these four cups and caps I've got. And I say it's cyclic if these two are actually equal. And then I define the transpose just to be the common morphism from X star to Y star. So that is the transpose. And then the trace property is that if we've got a morphism from Y to X and a morphism from X to Y, with one of them having a transpose, then we can do this little trick. So we can we take the trace of F composed with G, we can move this F round to the other side, so that'll be a dual at the back here. We can move it round to the back by using, let's see if I can see this here, by using, so what I need to do is I can just put a little squiggle in there, and if I put a little squiggle in there, a little zigzag, then I can then see that what I've got, in fact, is this thing here to multiply by that. So this is, if I just use that one, it's come in here, come round, do an F, and come back, which is exactly the same as that. And then I can use the other one here and say that actually it's the same as bringing it round the side here. And there's supposed to be equality between these three. Okay, so provided we've got a transpose, then it satisfies the trace property. And of course, in the category of vector spaces, this always happens. So usually, in most of the I don't know any examples where this doesn't, where this isn't the case. We have to sort of be explicit. Okay, so that's the situation for just monoidal categories. I've gone through in some painful detail. So with monoidal bicategories, to be slightly more careful. So now we've got a monoidal bicategory. So we've got objects in the monoidal bicategory. So we want the evaluation and the co-evaluation maps again. But we've got to be slightly more careful with the zigzag relation. So put this back up. So the standard mantra is that equalities become isomorphisms when you add sort of higher categorical levels. So here we've got two morphisms and some relation between them. So these things are equal, but when we add extra categorical structure, we're going to just ask for an isomorphism between these two things. So just as you never really deal with equal objects in a category, you only deal with isomorphic ones at best. Similarly, you rarely deal with equal one morphisms in a bicategory, you only deal with isomorphic ones at best. So what we have then is this cup and this cap together with two isomorphisms. Two isomorphisms. So this is an isomorphism. So again, we're reading our diagram upwards. So this is a map from the zigzag at the bottom just to the identity at the top. And similarly, we've got the zigzag at the bottom to the identity at the top. So we'll just press the on-off button.
Yeah, you just have to wait a little bit. Is it on? Oh.
Did you press the button twice? Trace was fine.
Okay, so these are supposed to be... there we go. Right. So I'm not very good at drawing these, so I actually got a computer to draw them for me. So here we see...
Sorry, could you go?
so you can see...
Sorry.
But this is going from zigzag bottom to the straight top.
One more time.
Sorry.
Okay. So that's actually on Google videos, not on YouTube. Find some way to link up to that. So these are two isomorphisms, so we also have their inverses. I've just drawn these, but I wanted to also specify a two morphism going the other direction, which is its inverse, which cancels out. Similarly, we've got that. So we replace those two zigzag equalities with these isomorphisms. And we're adding these extra data, and these extra data also have to satisfy some relation. So this one I'm really bad at drawing. So this is sort of saying that if we compose this with just the identity, so this is a two morphism, and this is just the identity two morphism on this cap here, that if we do it with one of these, so here I'm supposed to be using one of these, then these are actually equal two morphisms. So again, let me just show you. Right. So this is supposed to be what this picture is here. It's a little bent. Whoops. So you've just got a sort of a little dint inside this curved thing, and you just build it by just composing with these appropriately. So if you're going from the bottom to the top, if you go cross sections, then here you just start with just a cut. You introduce a little zigzag, and you move that zigzag round, and then you cancel it out at the other side. So that's sort of taking cross sections, so maybe that's a better way to see what's going on. And we have some more similar relations. So this is what we mean by a dual in a monoidal bicategory. So we don't have equality, we have isomorphisms between the one morphism instead, which satisfy some extra relations. No, it's fine. It's fine. Leave it.
Simon, how is it known that those are right?
How is it known
When
that
you
it's right?
when you go to sort of higher category stuff, you have to make up all these, not make up,
Yeah,
but you
because
have to.
the theorems are true.
Okay.
Yeah, the theorems you want are actually true. Thanks, Bob. Okay, so you also have the idea of a transpose. So if we have a one morphism, so a one morphism, well, the old definition. So the old definition was a very good filing system. So the old definition was it had a transpose if we had equality of these three things. These are one morphisms, we're in a bicategory, so we're never going to have equality. So we expect isomorphism between. So we say that we have a transpose if we have a given map from y dual to x dual, so we're going the other way but we take the duals, together with isomorphisms to the appropriate things with the zigzag bit. So this is the same picture as we had before, except we've just marked on this extra f on it. So we're going to give a specified one, and it's not going to be equal to the other ones, but it's just we're going to have canonical isomorphisms to them, and satisfying some conditions. Now from that, we can glue on, if you think of gluing on a little cap around the side here, and then a little cancellation, you get something like this. So you will get an isomorphism from, draw it on the side here, which is, so in the monoidal one category case, we have that, we have something like, if you put an f there, then that's equal to, putting f star on the other side, say x, be y, star, and again, we're not good, so that would be what happens in the one category case. In the monoidal one category, we're never going to get that. But having this data, we do get a canonical isomorphism between these two things. So now I can go back to my examples and answer Bob's question about dagger structures, in fact. So, the span, oops, everything has a bidual. If you start with the set, then its dual is just the set itself. I've just drawn on the evaluation, so we go from x cross x to the unit object. So, our evaluation is going from the thing to its, with the tension bidual to the unit object. We'll go x cross x to star, and you just take this thing. You just take x with the diagonal map, which has also been mentioned previously today. So, what about transposes? So if we have a one morphism from x to y, its transpose should be a map going the other way between the biduals. But the biduals are just the same thing, so it should just go the other way. So we just switch it around. So it's not a dagger structure. A dagger structure would be one layer up, would be another layer structure. But okay, so similarly, bimodules, the bidual of an algebra is just the opposite algebra. You just reverse the multiplication. And A itself, if you have an algebra A, then the algebra itself is an AA bimodule. It can act on its left and it's right on itself. But we can think of that as a right A tensor A op module, because this A op acting on the right by A op is the same as acting on the left by A. So we can just make A automatically into a bimodule for C on the left and A tensor A op on the right, just using the usual structure. And that turns out to be the evaluation map going, which makes that into a bimodule. And similarly, the morphism is just a bimodule, and the transpose, you just switch them around, and as I've just said, a left A op module is exactly the same as a right A module and vice versa. So you just take the same thing, except you just pretend that this A is acting as its opposite on the left rather than on the right. Similarly, again, I won't go into the details of the enriched Prey-Functor case, but that's pretty much the same as the bimodule case. So two tangles. Just have a set of points. I could be slightly more careful about whether these have orientation or not. The bidual is the same set of points, or the same set of points with reversed orientation, depends if you take your tangles to have orientations or not. The evaluation, well, you just draw the strings that here we've got a set of points, here we've got the dual, we've tensored them together, just take the disjoint union. So the evaluation is just take the tangle, which is just this portion. We have a morphism. So this is supposed to be a tangle hidden inside here. So all we do is we rotate it through 180 degrees, and that will be the transpose. And you can see that if you put a horseshoe on that side and a horseshoe on that side, and you pull it straight, then you'll get that. And it would work whichever way around you put the horseshoes. So, and you generally, I mean, this thing with the isomorphisms, you genuinely do need to use isomorphisms rather than equalities. Again, with the varieties, it's a simple picture. In this case, the manifold is its own bidual, structure sheaf of the diagonal. If we have a sheaf over x cross y, we just think of it as a sheaf over y cross x. So we just get a map from y to x, we just think of it as a map from x to y. So just this symmetry kicking around. And similarly with bimodules, again, it's an analogous picture, with the derived version of bimodules. How long have we been going, Bob?
42 minutes.
42 minutes, right. Okay. Right, so we're now in the situation where we can just do the same thing. We can just take traces if we have biduals. Okay, so if we're in a I-category, monoidal bicategory, and object has a bidual, we can do exactly the same thing as we did before, and we just take a trace the same way. Okay. And now, what happens to the trace property? So again, you look at the proof we had before. We said that if we have two morphisms which compose to give an endomorphism, then the trace of F composed with G was the trace of G composed with F, because we had this sequence of equalities. We don't have a sequence of equalities, now we have an isomorphism. And this is going to be often an interesting isomorphism. These are not going to be equal in general. You're going to get an isomorphism between them. So you can just write down this little cobordism here using the structure I just gave you. That's what this little two-morphism is on the side there, and you get a isomorphism between the traces. So that's what the trace property becomes in this case. And just one other thing is that I'm not sure if this is useful yet or not, but if we have a cyclic morphism, a morphism with a transpose, you actually get an endomorphism of the trace. It comes for free. You can just push this thing around the back of the circle. course, this would just give you an equality in the monoidal category case, but here you get a this is a two isomorphism from the trace of E to the trace of E. So I'm calling this the round trace because it looks round. So that's what this little arrow is. It's supposed to be a circle, not a zero. This is the round trace. So that's pretty much the same as what you get in the monoidal case, but we can do something kind of different. So we can also take another trace. So this is the sort of surprising thing about bicategories. So this will work in a bicategory where you don't have any monoidal structure. So for X, an object of a bicategory, and if you have an endomorphism, then you can just take this diagonal trace and you just define it to be the two homomorphisms from the identity to your endomorphism. So here, sort of picture it pictorially like this. So we've got a two morphism from the identity, so nothing is going on at the bottom, and we've just got the endomorphism E at the top, and we've got a two morphism theta going from one to the other. So this is of quite different character to the other trace. I mean, the other trace was a one morphism from the unit object to the unit object. Here what you've got is a set of two morphisms. So these look to be of quite different nature. I mean, this is the thing that actually crops up, not got the time to go into it, but for instance in Bruce's thesis, I mean, when you're looking at group actions on two categories or something, this is the right way to define characters of representations of groups. This is the right notion of trace to look at there. And it's not the one you're necessarily used to thinking of if you're used to thinking of monoidal one categories. So this is a different kind of trace. And so how does the trace property come in here? Well, if we have a two morphism from the identity to some product of two things, so we would just picture it like this. So it goes from the identity, and we get this two morphism to P composed with Q. If we have an element inside here, if we have something in our two trace, we can just stick it inside the gap. This is just composition. This is just composition of two morphisms in R2 category. And this will give us an element from nothing, from the identity, to P composed with E composed with Q. So we get a trace of, we get a morphism from, this is just, in this case, a set map from this diagonal trace to this other diagonal trace. And in particular, if we have an equivalence, so if Q is invertible, if we have a one morphism which is invertible up to a two morphism, then we're going to get, if it's an equivalence, then we get the isomorphism from the identity to Q composed with Q inverse composed with Q, and so we get an isomorphism from trace of E to this conjugated E. So this is the other sort of version of this trace identity. So you don't get the other trace identity EF equals FE, or isomorphic to FE in this case. You get this other version. So this is a slightly different trace. Okay, so now let's go back to the example. So these are looking quite different. So if we have an endomorphism in span, so this is just a map to X cross X, what the round trace is just the loops in there. So if we have, let me just draw what's going on. So if we've got some set X, an endomorphism, you can just think each element in Z is going, if we call this, say, the tail and this the head, then you can think of each element in Z as just being and what what the round trace is it turns out to just be the loop. So it's just you just take the set of all elements in Z which have the same head and tail. And the diagonal trace is a choice of loop for each element in N. So that could well be empty. I'll learn a bit later. Now, for our bimodules, turns out, so an endomorphism is just an AA bimodule. The round trace of such a thing is the space of co-invariance. So this is M modulo MA equals AM for all elements in the alpha A. And the diagonal trace looks very similar, quite bizarrely, even though I've defined it completely different. These are the elements in M which commute with all elements in A. So this is the so-called invariance inside A. So there's some strange duality going on that really you wouldn't necessarily expect given the different natures of these two traces. So in the, and this sort of generalises to the enriched profunctor setting where you get some end and some co-end, which I won't go into. In the two-tangle case, the things look quite different. So an endomorphism is just a tangle with the same number of endpoints on each side. And taking the round trace, you just take the link closure, so you just end up with a link. And here you just take all the cobordisms from just the straight braid into your tangle. So this is a set of tangles, a set of cobordisms, the diagonal trace. The round trace is just a link. So they're quite different. These are very, very similar. These are quite different. And what I would consider the interesting cases, these two at the bottom. This is kind of strange, but I won't go into this. So the round trace for complexes of sheaves over x cross x is the Hochschild homology. The diagonal trace is the Hochschild cohomology. So they really are dual in that case. And the same with the bimodule picture. And this is related, so these are sort of jazzed up versions of this. This is sort of H0, this is the zeroth Hochschild homology, this is the zeroth Hochschild cohomology. So it's sort of jazzed up versions of that. But this is what really piqued my interest in these two different traces, is this relation between the two. Okay, so just finishing off then. We can take the dimension. So every object has a canonical endomorphism associated to it, which is just the identity. So any object in our I category, we can just take the identity morphism from x to x, and dimension is just the trace of the identity. That's certainly the definition. Well, it's certainly a theorem for vector spaces anyway, finite dimensional vector spaces. So this sounds like a good definition. Take the identity, take the trace, and we'll define that to be the dimension. So we get to each object in a monoidal bicategory, if it's provided it's got bidual, then we have these two notions of dimension. We have the round dimension and the diagonal dimension. And again, they're of different nature. This is a one morphism. This is a set of two morphisms. But you get certain relations between them. So, the first thing to note is that the diagonal dimension is a commutative monoid. So you can just compose these. If you've got two elements in here, you can just compose them as two morphisms, and the Ekman-Hilton argument tells you that this is actually commutative. But then you get a relation between them, which the diagonal dimension actually acts on the round dimension. So if we just have an element in the diagonal dimension there, then we can just draw this this two-morphism from the round dimension to itself, and we just stick that two-morphism in the middle there, which is that element of the diagonal. So we get, this is a commutative monoid which acts on the round dimension. So then, just to finish off, I should just tell you what these things are in the cases that we had. So associated to any set, unfortunately we don't get to anything very interesting. So the round dimension is supposed to be a morphism from a span from the one element set to itself. So a span from one element set to itself is just a set. So, in fact, the round dimension of the set x is just x, and the diagonal dimension, so this is supposed to be a monoid which is acting on x, and it's a rather dull monoid acting on x, so it's just a one element monoid. Okay, for an algebra, we start with an algebra. The round dimension of an algebra, thought of in BIM, is just the abelianization of the algebra, and the diagonal dimension is the center of the algebra. So this is a good commutative monoid, the center of an algebra. For an enriched category setting, we get again the end and the coend, but you can actually write down these slightly more explicitly. The diagonal dimension is the set of natural transformations from the identity on your category to itself. Two tangles, just get some cobordisms and some unlinks here. But in this case, we get as an algebra, we get the Hochschild cohomology, which is sort of well known to be an algebra, and it's known that this acts on the Hochschild homology, and this is exactly the structure we're getting here. So this is where I really sort of came into it, to realise that this structure was just coming from sort of two categorical kind of perspectives. So you get the same picture with the derived version of bimodules as well. Okay, so I guess I'll rush through a little bit at the end there. So I guess just to sort of look into the future, I mean, Bob was asking about dagger structure, so there are sort of interesting dagger structures kicking around there which give more structures, for instance, on Hochschild homology and other things.
Are there any questions, comments? Bruce?
So some with the span, you could make everything G equivariant or something, and then you get like fixed points and stuff coming out from the round traces.
Yes. So I guess I wrote down this example somewhere. Yeah. So here I said you can take. So if you have a map from x to x, just f, we can think of this as a span from x to x in that way. So I didn't actually say this. So we can take the round trace of this, and this will just be the loops. What I said was the loops. In fact, as a set, this is precisely the set of fixed points of this map F. So if this is just an ordinary map of sets, then the round trace is precisely equal to the set of fixed points.
Is it possible one exist and the other not to exist?
Yeah, I guess if you don't have something that's dualizable, so I specifically wrote down things which all have bidual.
Okay, so if is either stronger than the other in the sense that if the round trace, the diagonal trace will definitely exist, or
so
vice
the
versa.
diagonal trace always exists. Yeah.
Right. Okay.
So that one's that one always exists.
Okay, that's interesting.
Yeah, you don't need a monoidal structure to define the diagonal trace.
So I saw that in span that compact structure is actually a comonoid of the underlying category, or it doesn't have any extra structure there. You had some multiplication, you had unit, but there is no extra structure that comes in any way.
No.
Okay, that is it. No other questions?